We started off the past 10 lectures or so with a reasonably detailed model of synchronous machine. In fact, we considered several windings on the rotor. I mean, in fact, one can imagine that the simplest model which could give most of the correct information, most correct information of how a synchronous machine behaves, especially in steady state, etc., can be got without considering damper windings, because eventually the current goes down to 0. Of course, during transient conditions as well, it would be useful to work out some simple models of a synchronous machine. So that there are three reasons why one can look for simplified models. One, of course, is that the data for detailed models may not be available. We may not get all the standard parameters. Sometimes in our studies, this kind of data is not available. On the other hand, one would like to have all this data and use a detailed model. In some cases, of course, you will find that you can model a generator by a more simple model than what we have considered. For example, hydro turbines, it turns out, can be represented by one less damper winding on the Q axis. So, one can actually work with a simplified model, which is suitable for a hydro turbine. Okay. Of course, if one wants to do a theoretical analysis and try to get information about phenomena without worrying too much about getting a great deal of accuracy, in that case one may wish to work with lower order models. They seem to give better insight. Right now, of course, if we look at our synchronous machine model, it contains a large number of equations. Okay. So, you have got, in fact, if you consider the 0 sequence equations as well, you will have 7 flux equations, 7 differential equations of flux, okay, in addition to the electromechanical equations. And as we shall see later in this course, when you consider an integrated power systems, you have got lots of synchronous machines and so on. So, what you will find is that the number of equations becomes quite large, and one may not be able to do any kind of theoretical or a kind of insightful analysis into a synchronous machine without invoking fairly detailed and sophisticated numerical tools. Okay. So, I think it is worthwhile to look at somewhat simplified synchronous machine models, which ignore one or the other damper winding. In fact, actually we have already worked out one simplification, which is okay when we study slow transients, that is replacing d psi d by dt and d psi q by dt is equal to 0 and converting the corresponding equations into algebraic equation. That was one simplification which we did, which was justifiable in case one used one was really interested in only slow transients. Okay. So, that is one thing which we have already done. What we will do now in this in today's lecture, come up with more simple models in which we will be neglecting one or the other damper winding, or even we may neglect all the damper windings and come up with a simple model. Now, one interesting thing which I want to do by the end of this lecture is using the model which we have derived using 2 damper windings on the Q axis and 1 on the D axis along with the field winding. I want to come to a point where I can show you that you can get what is known as the classical model of a synchronous machine, which we have used to derive or rather understand some important phenomena right in the beginning of the course. Okay. So, what are the approximations involved in getting such a simplified model of a synchronous machine? So, that is something we will try to understand by the end of this by this lecture. Okay. Now, so today's lecture is titled Simplified Synchronous Machine Models. Just one small point about the kind of terminology we will be using. We have derived what is known as, or we shall call as, the 2.2 model of a synchronous machine. A 2.2 model of a synchronous machine involves 2 damper windings on the Q axis This of course refers to the rotor windings. Okay. and one damper winding and one field winding on the D axis. Okay. This is a fairly detailed model. It is quite a respectable model to use, especially for steam turbine driven generators. Okay. Round rotor generators, normally we would use such a full blown model. Okay. Now, what if we want to get a simplified model? In fact, before I go ahead with trying to reduce the number of rotor windings and getting simplified models with lesser number of rotor windings, let us look at one of the approximations we have already made, just for the sake of revision. Okay. So, let us just first look at the Q axis per unit model. Okay. So, we will just look at what we have so far in the 2.2 model. We have got two differential equations corresponding to the two damper windings in the Q axis. We have an algebraic relationship relating psi q to the current and psi k and psi g, and we have of course a differential equation in psi q, d psi q by dt. Okay. Now, in the d axis, with an assumption, okay, that T d c double dash is equal to T d double dash, we have a similar model. Okay. But of course, one of the windings here is the field winding. Okay. The field winding is of course affected by what voltage you apply to the field. Okay. So, that the effect of the field winding in these per unit equations is captured by EFD. Okay. So, if you look at what EFD is, it is of course related to the field voltage which is applied at the field winding. Okay. Of course, we have zero sequence equations as well, which you may require to use in case you are doing unbalanced analysis. Okay. And we have the torque equation in per unit, that is relating the rate of change of the speed of the synchronous machine with the electromagnetic torque, which is a function of course of the fluxes and currents. Okay. So, this is where we are. Okay. This is a kind of Mount Everest of synchronous machine modeling. Now, we slide down Mount Everest and we look at approximate models. Okay. One of the models which you have already kind of beaten to death, or rather one approximation which you have considered fairly in the past 2 or 3 lectures, was replacing the d psi d by dt and d psi q by dt differential equation by algebraic equations. This was done simply by setting d psi d by dt equal to 0 and d psi q by dt equal to 0. So, in that equation we just replace d psi d by dt equal to 0 and d psi q by dt equal to 0. So, this is an approximation which is valid in case we are talking of slow electromechanical transients. Okay. Slow electromechanical transients, the swings which we were discussing in some of the lectures. Okay. Now, while operating near the nominal speed, we could, if we are all our electromechanical transients in fact are taking place if we are near the nominal speed, we could in this particular equation replace omega by omega b. Okay. So, that becomes kind of a constant multiplication factor. Okay. Now, this kind of approximate model can be used if you are of course near the nominal speed. You cannot use this approximation of omega approximately being equal to omega b if you are trying to simulate or understand a synchronous machine right from the process of synchronization. Okay. That is starting rolling the generator and getting it near the synchronous speed. When the speed is not too close to the synchronous speed, we cannot make that approximation of omega being approximately equal to omega b in this particular equation. Okay. But as I mentioned, if you are talking of transients in which you are not going to deviate too much from 50 hertz or 60 hertz, whatever your nominal speed may be, then of course, this equation is valid. Okay. If one is studying slow transients. So, this is one of the approximations that we have made, and we saw that it did not make much of a difference during our short circuit studies. In fact, it made some difference all right, but it did not affect the modes associated with the slow transients. So, that was the basic effect of this approximation. Of course, do not make this approximation if you are going to study fast transients, say which occur in time scales of 1 or 2 cycles. Of course, that would not be correct It wouldn't be right to set d psi d by dt and d psi q by dt equal to 0 in that case. Okay. So, this is one approximate model which we have done. We move on to making approximations not in the stator coils, psi d and psi q of course are stator coils. What we will do is makes a few approximations as far as the rotor coils are concerned. So, the simplest thing we can do is one of the damper windings the effect of it is neglected. So, for doing that what we need to do is consider one less damper winding in our original derivation of the synchronous machine model. But rather than of course redoing the whole derivation again, a simple thing which can be done is of course open that particular damper winding. So, suppose you have of course got the D and Q windings. So, in the Q axis rotor windings are of course 2, the G and the K winding, and there is a field winding and a damper winding on the D axis. What I need to do is in this particular model, in order to simplify it, is get rid of this effect of this winding. So, what you can do of course is set the resistance of this winding. For example, this winding R k, if the winding R k, I set the resistance to be a very large value. In that case, it is as good as opening the damper winding, in which case of course no current will flow in the damper winding, that particular damper winding, and its effect is would get nullified. Okay. Now, important point which you should note is that when I set R k tending to infinity, what effectively happens to the time constants, that is something I leave as an exercise to you, but you can show that in such a case T q double dash tends to 0. So, if R k tends to infinity, T q double dash tends to 0. How do I know that? Well, I know the equations relating the time constants, okay, time constants in the standard parameter model, standard parameters with the original inductances and resistances of the winding. Recall this, we have done it somewhere in the between the 10th and the 20th lecture, where we were modeling synchronous machines. Okay. Now, so setting R k tending to infinity would mean that you are setting T q double dash tending to 0. Okay. Now, if you do that, what happens? So, if you look at the basic equation which is there, you can write this in fact as T q double dash is equal to minus psi k plus psi d. Okay. So, this is the equation which is there of the flux of this particular winding, and if T q double dash tends to 0, you can roughly say that this term here becomes 0, and as a result of it psi k becomes equal to psi d. So, from this you get this. Okay. Now, if psi k is equal to psi d, you can replace psi k by psi t in the algebraic relationship which relates psi d, psi q, I q, psi g and psi k. Okay. So, do you recall that equation? We will just have a look at it right away. So, what I am trying to say is of course that you get psi k is equal to, I am sorry, it should be psi k equals to psi q. This is some small error which I made while writing this. This should have been psi q, this should have been psi q. Yeah. So, getting back to the slide which I have, you get psi k is equal to psi q. So, you can substitute psi k by psi q here in this algebraic equation. The third equation is an algebraic equation, and then if you do that, you can write psi q as a function of I q, something into I q plus something into psi g. So, the effect of psi k gets subsumed in psi q. Okay. So, what are these coefficients here and here? you can work it out. I will just write down what you get eventually. What you will get eventually is, if you look at the slide, your equations of the 2.1 model, 2.1 because now we have got just one damper winding on the q axis, will be given by one differential equation corresponding to psi g. One of course, is corresponding to psi q, and the algebraic equation relating psi q, I q and psi g becomes much simpler, and you will notice that x q double dash no longer appears in this equation. So, for this particular model 2.1 model, you do not require one set of time constants and one set of basically you will not require one time constant and one reactance. Okay. So, it does not figure in the equations any longer. Okay. If you look at the slides again, the last equation of course, is still the differential equation in the flux psi q. Remember that you can make an approximation that you can replace d psi q by dt equal to 0 and get back to the approximation which we mentioned right at the beginning of this beginnings of this lecture. Okay. That would be okay if you are studying slow transients. So, the last equation also could be simplified in case you are talking about slow transients. Okay. Now, one of the things which I should mention at this point is that the model 2.1 model which I just discussed so far is found to be adequate in the sense that it can represent the transients which occur in hydro turbine driven synchronous generators. Okay. So, hydro turbine synchronous generators are often represented by 2.1 model, and do not be surprised if the data sheet of a hydro turbine generator has one less time constant and one less reactance. Okay. So, that particular data will not be given because it is adequate to model a hydro turbine just by 2.1 model. Okay. So, this is something you ought to keep in mind. Now, an interesting observation here which you may have noticed is that if you look at the algebraic equation relating psi q and psi g and I q, of course, it does not contain x q double dash, there is no need of having x q double dash, but if you look at the algebraic equation, so I will just write it down here, psi q is equal to x q dash I q plus x q minus x q dash upon x q into psi g. If you look at this particular equation and compare it with the algebraic equation which we had for 2.2 model. So, if you look at the screen here, you will see that the equation which was there before, I will just write it a bit quickly out here. Well, it looks pretty complicated, but something you will probably able to suggest is that if I had directly set x q double dash is equal to x q dash in this equation, in that case you would have directly got this equation. Note that this term would have disappeared. This is in fact dash. So, this would be 1. So, we would be really getting back to these equations. So, an interesting observation here is that if I want to go from 2.2 model, that is the original 2 dampers on the q axis model, to 1 damper winding on the q axis, then what you can do actually is simply set simply set x q double dash is equal to x q dash in the 2.2 model equations. Now, why am I telling you to do this? Well, you may have already written a program or a kind of a tool which does eigenvalue analysis or synchronization, the simulation numerical integration of the differential equations in the 2.2 model, and somebody tells you suddenly, well, a particular generator has to model not by 2.2 model, but it has to model by 2.1 model. In that case, you do not have to rewrite your program with lesser number of equations, you would need to tinker with your program. Instead of doing that, you just set x q double dash is equal to x q dash in the data. Okay. So, just look at these equations again, you will find that because of doing this, you will get rid of the effect of psi k. Okay. Of course, this equation would still be there, but it would be kind of decoupled from means the effect of psi k would not be effectively seen by a synchronous generator stator windings at all. Okay. So, there is no harm in just setting x q double dash is equal to x q dash and removing the coupling which psi k has with the rest of the equations. So, this is a pragmatic way of using a program or a tool which is programmed for 2.2 model, directly make it suitable for use with 2.1 model. Just set x q double dash is equal to x q dash. Okay. Of course, you need not do it, you can actually even do another thing, that is reprogram everything for a lower order model, that is also possible. So, in case you do that, you will have to use these equations, the lesser number of equations in your programming. Okay. So, this is what basically is you do when you neglect the effect of one damper on the q axis. Now, before we go ahead, let us just see what happens in case we try to simulate a system with a lower order model, okay, of a synchronous machine. So, what we will do is take the data which we have been using for studying the synchronization transient. In fact, the data is for a round rotor machine, but all the same we will still use it for just comparing what happens in case you take a simplified model. So, what I will do is I have programmed it, I have programmed the program for 2.2 model, but I will simply make the simplification x q double dash is equal to x q dash and effectively get 2.1 model. Okay. So, I will just do that. So, we will get back to our Scilab program, and what I will do is, of course, first of all show you the original speed transient under synchronization. We have been doing this in the past few lectures. So, I need not explain everything right from scratch. It is basically a transient which shows the synchronization of a synchronous machine to an infinite bus, followed by torque and field voltage increases. Okay. So, this is increase in torque and field voltage. So, these are the transients which you see. Now, in case you take this program and in that set x q double dash, which is here, equal to x q dash. So, if you do that, how does it affect? So, let us just try if we can do it. Of course, we have to hope and pray that, so the program runs without any problem. It is just, we have just changed the data, we have not really changed anything in the program. Okay. So, if I plot this now and look at what we get, well, you notice something. Well, the original program, the damping was much higher, okay, whereas now in all the transients which are considered, one thing you can notice is that the transient takes a longer time to die down. In fact, in a synchronous machine with one damper winding less, it appears that the damping has reduced. This is not very surprising. In fact, one may say that the damper winding derives its name in some sense from the damping effect that it has. So, if we actually reduce the amount of damping, in that case, that is by removing one damper, it is not surprising that we get this larger time for decay. of the transient. Okay. So, this is something which is not at all surprising. This is effectively the response we will get. The top one which you see here, the one which is taking a long time to die, is effectively the response without a damper winding, one of the damper windings. Okay. So, let us go back and also do the eigen analysis. We will do exactly the same thing and do an eigen analysis, eigenvalue analysis using a linearized model, which we discussed in the previous class. So, now I will just run the program. Okay. So, I just take out the eigenvalues, and the eigenvalues are these. Well, not much can be understood from this unless we compare it with the eigenvalues with the 2.2 model. So, what I just now showed you were the eigenvalues with 2.1 model. I will rerun the program to see the eigenvalues with 2.1 model. So, what you notice here of course is that there is a significant change in the real part of the eigenvalue corresponding to the electromechanical oscillation which is seen in the speed transient. Okay. So, this is consistent with what we have seen before. In fact, of course, we need to just check out the operating point which we are talking of. Yeah. So, what we see here is of course, that if I take 2.2 model, the real part of the eigenvalue is 1.4 roughly, whereas the eigenvalue here is 1. So, you see that with 2.1 model, the damping of the swing mode is slightly lower. Okay. So, this is something it seems to be consistent with what we see here. We see a slower rate of decay when we consider a lower order model. Okay. Now, remember here that we are not doing any closed loop feedback control of the field voltage. The field voltage is practically a constant. We are either giving step changes or we are keeping it a constant. We shall see later in the later part of this course that the feedback control of the field voltage in a synchronous machine can again affect the damping of the electromechanical or what is known as the swing mode. Okay, that oscillatory mode, which is has a frequency of around 10 radian, that is 12 radians per second here. Okay. Now, let us go one step ahead. Let us go to a model. Now, what I will do is go a bit faster and talk about what next can be done. You can in fact go to what is known as the 1.1 model. In 1.1 model, we have done the corresponding thing with the damper winding H. So, what I have done is set R H tending to infinity and therefore, got rid of the differential equation corresponding to psi capital K, and as a result of which we get a simplified model with just one differential equation. And as I mentioned last time, the same thing can be done here. You can get this lower order model directly by setting x d double dash is equal to x d dash. So, if you have already programmed 2.1 model or 2.2 model to get to 1.1 model, all you need to do in that program is to set x d double dash is equal to x d dash. Alternatively, you can program a lower order model. Okay. So, both these things can be actually done. Okay. We can go one step further. We can actually get rid of the last remaining winding, damper winding on the q axis. Okay. That is the G winding. But at this point, let us just take a small diversion, not a very big one. If from this 1.1 model, a 1.1 model means you will be using these equations on the q axis and these equations on the d axis. Okay. So, that is 1.1 model. I will show it to you again. You will be using these equations in the q axis and these equations in the d axis. Okay. Now, one question which I would like to ask you is, can we get the equations of an induction machine from 1.1 model of a synchronous machine? The answer is yes. From the 1.1 model, equate x t dash and x q dash. Okay. An induction machine can be modeled, a simple induction machine model could be by considering one damper winding on the d axis and one damper winding on the q axis. Remember, induction machine does not have any field winding. So, what you can do is, of course, these windings are absolutely symmetric. If you look at a normal synchronous induction machine, both the d and the q axis appear similar, there is nothing to distinguish a d and q winding. So, you need to set this, I will call it x dash, and what you need to do is, of course, do this, equate. Effectively what I have done is got from 1.1 model simply by setting x d dash is equal to x q dash and t d dash is equal to t dash is equal to t dash is equal to t q dash. Okay. You can in fact from the 1.1 model get a induction machine model. Okay. So, 1.1 model of a synchronous machine can directly yield to you the induction machine model. You will of course have to set EFD is equal to 0, this is something you need to do, okay, and effectively equate the D and Q axis parameters, set EFD also equal to 0. So, these are the things you would need to do in case you wanted to derive an induction machine model directly from 1.1 model of a synchronous machine. Okay. So, this is interesting diversion which is apt at this point. Okay. Now, we can go ahead and get rid of even the remaining damper winding on the q axis. So, what we are going to do now is talk about a simplified synchronous machine model which does not have any damper winding at all. Okay. So, this is the what you will get. Effectively what you have done is set T q dash tending to 0. Basically, if you have R g tending to infinity, that is your opening the last remaining winding of the q axis, in that case T q dash tends to infinity, and in that case we can kind of convert the differential equation corresponding to the g winding, that is d psi g by dt T q dash is equal to psi g plus psi q, and if you do that, if you set d q T q dash tending to 0, in that case you will get psi g is equal to psi q, and if you use this fact in the algebraic equations which you have seen earlier, say if you look at the 2.1 model, if you look at this algebraic equation here, if you set psi g is equal to psi q, a few manipulations will get you to psi q is equal to x q I q. So, what you have in the q axis is just one algebraic equation and one differential equation corresponding to the stator winding, that is psi q. Okay. So, one differential equation and one algebraic equation. In fact, the differential equation also can be removed by setting d psi q by dt is equal to 0 in case you are studying slow transients. Okay. So, this is what you get as 1.0 model. In fact, 1.0 model equations will have the d axis equations looking like this and the q axis equations looking like this. So, that effectively tells you what is the 1.0 model of a synchronous machine. In fact, this is you can say the last or the most basic of synchronous machine models, where you are now you have just the field winding and the stator windings, and all the damper windings have been got rid of. Okay. Now, if you look at the behavior of a 1.0 model synchronous machine, so what I do is in this generators program, I set to get 1.0 model, what I need to do is set first x t double dash is equal to x t dash, That is what I have done first. Okay. The second thing you can do directly, something which I have not mentioned here, is that in the 2.1 q axis equations, if I directly set x q dash is equal to x q, you can get rid of, you can really come directly to this algebraic equation and 1.0 model. So, that is what I will do right now. What we will have here is, I will set x q dash equal to x q, and of course, I also need to set x q double dash is equal to x q. So, that we get 1.0 model. Okay. So, this is 1.0 model, x q double dash is equal to x q dash is equal to x q. So, by doing this, we are directly modifying a program, we are not without modifying the program of 2.2 model, we can effectively get the response of the simplified generator model, and I have also said x d double dash is equal to x t dash. So, let us try to simulate this in Scilab. Yeah. And if I plot this now, yeah, you get a totally different response. In fact, what you are seeing is that the system is losing synchronism. Okay. So, in case you, I will just, the response is completely different. Okay. So, of course, one of the reasons why this could be happening, let me just expand this view. Is a numerical reason. One of the reasons which why this could be happening is a numerical reason. That is, see, if you look at the first curve here, it is with 2.2, this one is with 2.1. Okay. Now, we have gone to 1.0 and you see growing oscillations. Now, is this correct or not? Okay. That we can say by actually finding out the eigenvalues of the system. For example, we try to find out the eigenvalues of the system for 1.0 model. Okay. Yeah. So, I have modified the data so that, yeah, and we will take out the eigenvalues of the system. Now, what you notice is the real part of the eigenvalue has become quite small, it is minus 0.4. Okay. Now, one of the things you should remember here is that we are using Euler method to simulate the system, and if the damping, that the real part of an eigenvalue is low, Euler method may actually show it to be not a damped oscillation, but an increasing oscillation, and this is what exactly is happening here. So, although eigen analysis shows that the system is in fact stable, what you get here is a growing oscillation. Okay. So, growing oscillation of course, will eventually cause a loss of synchronism. So, this is kind of spurious, but remember one thing, that if we neglect the effect of all damper windings in 1.0 model, the damping of the swing mode may come down to a low enough value, not necessarily to make the system unstable as is seen in this eigen analysis, but which may cause misbehavior or other wrong information to be displayed in case we do a simulation using Euler method. Recall, in the first 10 lectures of this course, we have discussed numerical integration techniques, and there we did find, we did discuss this, that in case you use Euler method on a poorly damped system with a poorly damped oscillation, in that case you can in fact get wrong information. Now, the solution of this of course is to keep on reducing your time step of the simulation till Euler method starts giving reasonably correct results, but of course, that will take a long time to simulate if I really go on reducing my time step. Okay. So, one thing which you should remember now, it is important to, as a student to distinguish between two issues we are talking here. One is that with a lower order synchronous machine model 1.0 model, the amount of damping or the amount of rate of decay of the swing mode has come down substantially. That is one aspect, that is the physical aspect. One more aspect is about the analysis. The damping has really come down to such an extent that if you try to simulate Euler using Euler method with a time step of, we will just I just forgot what the name of the variable is for time step, I will just get that. Okay, with a time step of 0.005, a system with a poorly damped oscillation like this one is likely to show. So, let us just see this again, T step. Yeah. A system which has poor damping is likely to show is likely to cause incorrect information being shown in a simulation in which Euler method is used with a time step of this kind. Okay. So, really what you need to do, as I mentioned some time back, is go on reducing the time step or use a better numerical integration method. But of course, we have been using Euler method simply because it is an easy method to use. It is sacrilegious to use Euler method for any realistic or practical or industry grade program. I mean, because of this particular problem, that is not very accurate, it can give wrong information. So, this is another illustration of this. Okay. So, although the system is stable, remember all the eigenvalues for all operating points, this of course, the eigenvalues for a particular operating point. The eigenvalues have negative real parts. So, it is a stable system, but simulating it may result in problems if you are using methods like Euler method. So, that is the summary of what we have been discussing so far. Now, 1.0 model in some sense is the limit of what simplification we can have in a synchronous machine. If we want to get even a realistic picture in steady state, you have to use, at worst you will use this simplified model. Okay. Of course, for theoretical studies involving the swing mode, we can use a simplified model which includes no differential equation, no electrical differential equation, okay, no equation, differential equation corresponding to the flux. How do we get to that model? Well, this is not a very respectable model, because, so I will just tell you how you can get to what is known as 0.0 model, which is what is known as a classical model. A classical model is not a respectable model for getting realistic and quantitatively correct answers as far as synchronous machine behavior is concerned. For example, you cannot use classical model to understand the nuances of what happens during a short circuit in a synchronous generator. Okay. So, there are very great limitations in applying this classical model, but all the same I will just tell you what it is and how it is obtained and what kind of assumptions are inherent when you get to classical model. Remember that right in the beginning of the course, when I was talking about introducing you to things like loss of synchronism and the origin of swings, power swings or rotor angle swings in a power system, I had used in fact the classical model. It is not a respectable model, I called it a toy model then, I will call it a toy model even now. Okay. But let us just see what really was involved in getting to this classical model. What you need to do is, from 1.0 model, you can look at the screen again, from 1.0 model, 1.0 model requires these equations on the d axis and these equations in the q axis. What you do is, you assume that the field winding resistance is very small, as a result of which you can show using the basic equations which relate the standard parameters and the resistance and inductance parameters of a synchronous machine, you can show that T d dash becomes a very large value, it becomes tending to infinity. Okay. If T d dash tends to infinity, you are in effect saying that the field winding flux does not change. Okay. So, psi f here, okay, is 0, d psi f by dt is equal to 0. So, psi f becomes a constant. So, what you have is, you have got rid of the differential equation, the last remaining differential equation of the rotor field winding. Okay. You have effectively said that psi f is simply a constant. Okay. Now, a further simplification, of course, which we have been which I talked to right in the beginning, was you set C d psi d by dt equal to 0 as well. If you are going to study slow transients, this is an okay approximation to make. So, what you have eventually is, for the classical model, setting d psi d by dt and d psi q by dt, we have got this model. Okay. So, this is a classical model of a synchronous machine, which does not have any differential equation. No electrical differential equation. We have got the mechanical differential equations, but there is no electrical differential equation. And a further simplification which you can make is R A is equal to 0 and x q is equal to x t dash. Now, this is absolutely an ad hoc assumption. This is no kind of justification which I can give you. Okay. So, classical model is obtained by a large number of approximations. So, if you want to get from 2.2 model to classical model, you have really made a large number of approximations. So, what you will get, of course, if you just go ahead with what you have got, psi d is equal to x t dash I d plus E dash. E dash is that is actually proportional to psi f, which is assumed to be a constant. So, E dash is also a constant, and you also have psi q is equal to x t dash I q. This is got by approximating x q is equal to x t dash, an absolutely ad hoc assumption. Okay. We also have 0 is equal to, this is by neglecting d psi d and d psi q by dt terms. This is by neglecting d psi d by dt. We also make R A equal to 0. So, we will have minus omega b v d, and psi q we will also have is equal to omega b psi d minus omega b psi q. And what you can do is effectively substitute for psi d and psi q in these equations. So, what you will have eventually is, if you do that, you will have omega b will, okay. So, what you will have 0 is equal to minus of x t dash I q, okay, minus of v d, and what we will have here is x t dash I d plus E dash minus V q. Okay. Now, we also have d omega by dt 2h into d omega by dt by omega b into d omega by dt is equal to T m minus psi d I q minus psi q I d. Okay. Now, if you look at, so you have got these two algebraic equations and this differential equation. Now, if you are talking of a synchronous machine connected to an infinite bus or a stiff voltage source, okay, as the one which we have used for all our studies so far, in that case V d is equal to V line to line RMS of that source into sine delta minus of it. So, this is the source whose characteristics I have discussed in the previous lectures. So, if this is true, then it is easy to show, it is quite easy to show that psi d I q minus psi q I d from all the equations which we have got, from these equations, okay, and these equations, what you will get eventually is, this is the electromagnetic torque, is nothing but V line to line RMS by x d dash E dash sine delta. So, from this and this is what we have. So, the classical model effectively the torque equation or the electromechanical equations are d delta by dt is equal to omega minus omega naught. Omega naught is the frequency of the infinite bus, and you have got 2 h by omega b and d omega by dt is equal to T m minus V line to line RMS E dash sine delta upon x dash, and this is the transient reactance of the generator. Okay, we can call it just x dash. Okay. Now, another interesting thing is, of course, from these algebraic equations, if you look at these algebraic equations, you can write this very compactly. You will have E dash, okay, minus V q plus j V d. This is just multiplying the second equation by the complex number j, okay. E dash minus this is equal to j x dash is nothing but x d dash. We need not apply the subscript any longer because we have equated the dA and q axis completely. This is what we get, and you know from what we have here, we have V q plus j V d can be written compactly as V line to line RMS, okay, into e raised to, it is simply that, and just have a look at it. Okay. So, what we have here is eventually E dash into a minus V line to line RMS into e raised to minus j delta is equal to j into x I q plus j I d. And what we have from here effectively is E dash e raised to j delta minus V line to line RMS is equal to j x into I q plus j I d, where I q plus j I d is nothing but I q plus j I d into e raised to j delta. So, what we have here is effectively a synchronous machine model in which the electrical equations are simply given by this, or effectively an electrical circuit. So, what we have effectively is an electrical circuit. So, if you want to represent the synchronous machine electrical equations, it is simply a phasor, that is an algebraic equation. This is V line to line RMS of the infinite bus, this is E dash angle delta, and the differential equations are d delta by dt is equal to omega minus omega naught. Omega naught is the frequency of the infinite bus, and d omega by dt itself is nothing but T m minus E dash V line to line RMS sine delta by x dash. So, this is exactly the toy model which we used in this, in fact, right in the second lecture, okay, with the kind of model which we have used here. In fact, this model predicts an oscillatory response for delta and omega whenever there is a disturbance. So, what we have with 2.2 model is not only this electromechanical swing. In fact, if you recall, whenever you use a higher model with damper windings, the eigenvalues are these. So, there are many modes here. Okay. Amongst them, we have got what is known as the swing mode. If you take the classical model directly, what you will have is simply just because there are two differential equations, just one mode, and that will really represent, as we have seen right in the beginning where we did analyze this toy model, we do get the electromechanical oscillation. So, classical model is okay just to theoretically highlight the fact that you do have such a mode, which is mainly associated with the electromechanical variables delta and omega. Okay. So, just have a look at this classical model again. Yeah, this should have been x dash here. These are the differential equations. So, this is the classical model, which is okay, just okay for theoretical studies. Okay. But please do not, it probably will give you fairly, it will probably give you wrong quantitative answers, wrong in the sense highly imprecise answers in case you try to use it for practical studies. Okay. But nonetheless, just using the classical model, we can in fact show that a phenomena called swings occurs, okay, which is also evident in the 2.2 model, but the 2.2 model will also bring into picture many other modes which are present. Okay. So, this brings to an end, practically an end, our discussion of synchronous machines. We will just revisit a few minor points tomorrow in the next lecture. And thereafter, we will move on to another physical subsystem which is of importance in a power system, that is the excitation system of a synchronous machine. We will discuss its modeling and also discuss how it looks physically.